We're going to determine if the series, the summation from 1 to infinity of the square root of 3n cubed plus 4n plus 2 divided by the cube root or the third root of 5n to the 8th power plus 2n squared plus 10 converges or diverges. And we're going to use the limit comparison test, abbreviated from this point on by LCT. So here's a brief overview of the limit comparison test. Suppose we have two series, one summation of a sub n and the other summation of b sub n, with the restriction that an and bn terms are all positive, that is for all n. If we take the limit as n goes to infinity of an over bn, and that limit we computed, and that's equal to L, and L is a positive number, can't be zero, and finite, then the following holds. The two series converge, so either the series summation a sub n and series summation b sub n both converge, or the summation a sub n series and summation b sub n diverge. What we can have is one of them converges, the other diverges. So now we're going to utilize this test for this series at hand. We'll always call the series we are examining the a sub n series. So let summation from 1 to infinity a sub n be the series summation from 1 to infinity. In the numerator we have the square root of 3n cubed plus 4n plus 2, and divided by the cube root of 5n to the 8th power plus 2n squared plus 10. Now before we select the bn series and use the limit comparison test, what we want to do is rewrite the an series in a way that will make the selection of bn series easier. And what we're going to do is factor the highest power of n from each of the radicals. So in the numerator we have the square root of 3n cubed plus 4n plus 2. We're going to factor inside the radical the highest power of n we see there, which is n cubed, and that leaves a 3 plus 4 over n squared plus 2 over n cubed. And in the denominator we'll do the same thing with the radical, the cube radical there. The highest power of n we see inside it is n to the 8th, so that's what we'll do. We'll factor n to the 8th. That leaves a 5 plus 2 divided by n to the 6th plus 10 divided by n to the 8th power. Now the next step is to take square root of n cubed and the cube root of n to the 8th. So we'll rewrite this now as the summation from 1 to infinity. Square root of n cubed is n to the 3/2 times whatever was left, the square root of 3 plus 4 over n squared plus 2 over n cubed. The cube root of n to the 8th would be n raised to the 8/3 power, and then times the cube root of 5 plus 2 divided by n to the 6th plus 10 divided by n to the 8th. Notice that as n becomes larger and larger, those powers of n that are in the denominator, 2 over n to the 6th or 4 over n squared, they get smaller and smaller, so they will not be relevant as n becomes larger and larger. Now let's look at the highest power of n that we see in the denominator. Let's call that power d. Now the radical, the cube root, is irrelevant, so we look at the highest power of n outside the radical, and that happens to be 8 over 3. and let n be similarly the highest power of n in the numerator. That will be 3/2, and we're going to subtract the highest power of n in the numerator from that in the denominator. So this is common denominator is 6. That's 16 over 6 minus 9 over 6, and that will be 7 over 6. This 7 over 6 is a big clue how to select our BN series. We want to select our BN series to be the simplest series so that the difference between the highest power of n in the denominator and numerator is 7 over 6. And of course, such series, the easiest series that will work is the summation from 1 to infinity of 1 divided by n raised to the 7/6 power. And now let's go ahead and implement a limit comparison test. So we're going to take the limit as n goes to infinity of an divided by bn, and it turns out to be the limit as n goes to infinity. In the numerator, we have n to the 3/2 power times the square root of 3 plus 4 over n squared plus 2 over n cubed. And in the denominator, we have n to the 8/3 times the cube root of 5 plus 2 over n to the 6 plus 10 divided by n to the 8th. So that's a sub n, and our b sub n is 1 divided by n raised to the 7/6 power. And so what this will do from basic algebra, the way we would simplify this n to the 7/6 power will multiply n to the 3/2 up there in the numerator. So the net power of n is going to be 3 over 2 plus 7/6. We just computed this. This is going to be 16 over 6, which is equal to 8/3. That's what we want. And so the limit becomes limit as n goes to infinity. We have n raised to the 8/3 power in the numerator times the square root of 3 plus 4 over n squared plus 2 over n cubed. And in the denominator, we have also n raised to 8/3 power. So this is n to the 8/3 power. We can now cancel these, and we have the cube root of 5 plus 2 divided by n to the 6 plus 10 divided by n to the 8th. So now let's take the limit of what's left as n becomes larger and larger and larger. 4 over n squared, 2 over n cubed, 2 over n to the 6, and 10 over n to the 8th will all head to 0, and that leaves us with square root of 3 divided by the cube root of 5 as our limit L. Now that is a positive number. It is clearly finite. Therefore now we can conclude that the two series either converge together or diverge together. So let's rewrite the two series. We go back to the original form of the series. It was the series square root of 3n cubed plus 4n plus 2 divided by the cube root of 5n to the 8th plus 2n squared plus 10, and then the series summation n equals 1 to infinity 1 divided by n to the 7/6 power. Now we recognize the second series. It is a p series. P is equal to 7 over 6, which is greater than 1, and that means that the second series converges. This series is known to us. It converges, and now we can conclude that this series, the more complicated series, also converges, and we can state why by the limit comparison test.